Assalamu alaikum. Hi guys, this is the second part of slabs, and here I'm gonna be strictly speaking about the ribbed slab or the joist floors. Okay. First of all, I'm gonna start off with some of the provisions that are needed for one-way ribbed slabs, and these are you can find them in the ACI 19 code, chapter 9, which primarily deals with beams and ribbed slab. Okay. So, first of all, the width of ribs. I think I'm losing my mouse here. Okay, the width of ribs shall be at least 100 meters at any location along the depth. I will show you that on the next slide where I have a typical section of ribbed slab. The overall depth of ribs shall not exceed 3.5 times the minimum width. The clear spacing between ribs shall not exceed 750 millimeters. It's allowed to take the shear as 1.1 times the value that are calculated in 22.5, namely equations A, B, and C for phi VC. For structural integrity, at least one bottom bar in each joist shall be continuous and shall be anchored to develop Fy at the face of support, which means we're going to have at least one bar continuous throughout the 5 continuous beam, for instance. Then it should be continuous throughout, and we will talk about the anchorage and development length hopefully in the next chapter. So with that said, this is a typical ribbed slab from Jordan. Usually we have about 2.5 centimeters tiles. Then we have mortar, which is about 3.5 centimeters, some aggregate, which is about 9 centimeters, and then we have that thickness above the blocks. So this portion right here is what I call the rib. Typically in Jordan, it's from 12 to 15 centimeters. But as I said, the code usually allows for a minimum of 10. Okay. The height, the 3.5 or the maximum 3.5 is this height that I'm talking about. So let's say if I have 10 centimeters, then this should be at least 30, maximum should be 35 centimeters. Okay. The maximum distance or the clear distance between the rib is usually this distance. So if this is here starts the other rib, and here's the other rib. So this distance, which again, typical block in Jordan is about 40 centimeters. This can go up to 750 millimeters. Okay. As far as the height of the blocks, usually we have readily available the 18, 24, and 32. If you need other heights than that, then they need to be custom built. This 7 centimeter, this height of a flange, I would call, well, according to the code, if I'm using fillers, which is, let's say, block, and have the same F prime C as this portion over here, then the minimum distance or the minimum thickness, excuse me, should be at least 50 millimeters, or the clear spacing or clear distance over 12, and I'm calling that L over 12, where this is my L. So if I'm using, let's say, the maximum allowed, which is 750, divide that by 12, I think this comes about maybe 60 millimeters, and in Jordan typically we use 7 centimeters or 70 millimeters, so we are fine, and that's why we usually don't check it. Okay. Then also there's like about 2 centimeters of plastering, and I forgot to mention that. So how I'm going to analyze or design my rib slab, I'm going to analyze it as a T-beam. Again, this is from 12 to 15. This is 7 centimeters, and this could be 14. I don't think we use that anymore, but these are the most common ones. Again, if you want something else, you have to order it, special custom. Okay. So this is the typical T-beam. As you've noticed, this 52 to 55 centimeters is based on the 12 to 15. Again, with this being 20 and this being 20 centimeters. Okay. Again, that depends on the type of block that you are using, but this is what we use for design. With that, let's jump to an example right now. Here I want to design a ribbed slab with ACI again for 420 and F prime C is 21. Again, the rib is always in the direction of the short direction, so the loads are going this way and that way. So B4 and B3 are carrying the load of the slab. B1 and B2 actually they don't carry, don't have any. They carry only their own weight of the beam. Another thing I failed to mention, that ratio of the long span over short span being larger or equal to 2 is only for solid slabs. For ribbed slabs, this really does not apply, since you are controlling the direction of the load by choosing the direction of the rib. Okay, so please keep that in mind as well. So again, going back to a typical section, I want to estimate the B width. I want to know if I'm going to use 12 centimeters or 10 or 15. Here I'm going to assume cover 20, stirrups phi 8. Again, this is something related to how we design things in Jordan. Technically, you don't need any stirrups in ribbed slabs, but here we use about phi 8 every 20 centimeters. So it is there. So you have to count for it. If I'm assuming I have a main reinforcement of 2 phi 12, then the distance between reinforcement I'm assuming to be, let's say, 30 millimeters, which is again the max, just an assumption. Then from that I can calculate the B web that I'm going to use, which is right there, which is 2 times 20 plus 8 plus 12 plus the distance 30. I'm getting about 11 centimeters, so I'm going to use 12. As far as the height goes, here I have a simple ribbed slab. Again, here the beam and the ribbed slab have the same deflection criteria, so that's going to be L over 16. Here I'm having 3, again, since I'm using the clear distance, so this is about 18.75 centimeters. So this is the minimum that I require, since the height of my rib is about 18 centimeters, and I have the top mat about 7, so the total depth is about 25 centimeters, and that's what I'm going to use for the slab. So now to estimate the dead load, if I go to the rib, I'm using the area of a trapezoid, so that's about 1/2 times 0.12. This distance from here to here is about 0.19 times the height, 18, times the unit weight, so you're getting 0.67 kilonewton per meter. I'm going to take a study area of about 52 centimeters, again, which is my 20 plus 12 plus 20. So the total dead load from the rib is about 1.29 kilonewton per meter square. Here I'm just multiplying the thickness of the tires, the mortar, the aggregate with their respective unit weights, and I'm getting the weight per meter square. The plaster again is about 0.02. This is the unit weight for the plaster. The width of the block is about 1.44 kilonewton per meter square. Again, this is one study area. Height times the unit weight. The height of a flange, or the top mat, what we call here, is about 7 centimeters. Again, times the unit weight. I'm getting, for concrete, I'm getting 1.68 kilonewton per meter square. Now, adding all this up, I'm getting the dead load for the slab, which is about 805 kilonewton per meter square. Assuming that I'm having some partitions, so I'm going to add the dead load to that as 25. And this is straight from the ASCE, excuse me, 2016. So my total dead load is about 10.4 kilonewton per meter square. Here I'm just making an assumption for live load. So my total ultimate load is going to be 1.2 times the dead load plus 1.6 times the live load, and that's going to be 15.68 kilonewton per meter square. Thus the total load per rib is about 8.15 kilonewton per. Okay, now with the load figured out, now we can calculate the ultimate moment, which is simply WL square over 8. Here you've noticed I've used the center line to center line distance, which is half of the columns, which is 0.25 and 0.25. Now, technically you could use the clear distance, which is about 3, but the difference in the moment is really not that much. I mean, it's about 9 point something, but still I went with the bigger one. Usually in the exam, I will specify to you which length to use as far as the calculation of the moment is concerned. So you really don't need to worry. Since it's a regular T-beam, I'm going to assume first that the stress block is equal to the flange thickness, and that will be again 0.9, which is my phi, Fy, and this is my d minus height of a flange over 2. And this is the ultimate moment right there. So I'm getting 182.408 millimeters square. So I'm using that again to recalculate A, and I find that to be 8.25 millimeters, which is less than the height of a flange. So the assumption for my T-beam is correct, and it's going to be analyzed as a rectangular beam. Usually for a ribbed slab, it's about 90% of the time it does not fall below the thickness of the top mat. So here I'm using now 2π12, calculating a new A. It's giving me 10. C 12.04, net tensile strain. So this is again my phi is equal to 0.9 using raw web. Here I'm using the area of steel for 2π12. This is my B web 120 times D 216. And again, here just be mindful of using the phi 8 in calculating the D. Rechecking the ultimate moment. I'm getting 18.03 larger than M ultimate, so again, then this is okay. Calculating phi VC. Here I'm using again the 1.1, 0.75, 0.66, and this is again part C of the equation. It's giving me 13.32, which is larger than V ultimate. So again, as I said, technically you are not required to use stirrups in ribbed slab, but again, here in our country in Jordan, we are using the more than enough. I guess it's about like 5 stirrups per meter. Okay. So if you want to continue the design, then if you want to design the beams B3 and B4, then we use an ultimate load of 15.68 times 1.5. Again, half the slab since it's 3 meters. So that will be your ultimate load on the beams. If you want to design the columns, which we're going to get to hopefully maybe in the coming 2 weeks, then the axial load is going to be 82.32 kilonewton only. Forget this, it's not going to be mirror. Okay. So that will end the portion of the slabs. You guys enjoy your day and have a very safe day as well.